We're now going to consider the effect of the solvent in all of our electrochemical interactions. So when we think about solvent effects, remember that almost all chemistry happens in solvent, so the solutions account for most of these chemical reactions. Whenever you're in a lab doing synthetic chemistry, you have to dissolve the reactants which facilitate them coming into contact with each other. So understanding the behaviour of these solutions is absolutely essential to understanding more about the chemical reaction. Most electrochemistry experiments are done in water, but some measurements in organic solvents exist. So it's worth bearing in mind this is where we're going to be focusing our studies. And remember that a great deal of biochemistry happens in aqueous solutions. So inside the body we're predominantly aqueous with some lipid, but there's a lot of biochemistry that happens therein. So the first thing we're going to consider is concentration of solutions. So you've done a bit of this in your previous course with thermodynamics, but remember to recall the standard state. So we have this symbol here where we have standardized pressure, we have our standardized molality, which is moles per unit mass, and then we have our standardized concentration, which is moles per unit volume. In electrochemistry, we use molality, which carries the symbol M. The reason for this is that the mass of the solvent is independent of temperature. So when we start doing electrochemistry, solutions can expand, they can contract, and it's important to remember that as solutions are heated, the concentration, the molarity, will change, but the molality will not. So many factors affect the behaviour of these solutions, and we're going to cover a few of them in this session. The solution activity, which is one way of thinking of the effective concentration, is one of the key things that we're going to consider here. So many different things affect the behaviour. We introduced the ion-ion interactions, solvation spheres, but also the size of the ionic atmosphere. So all of these things affect the behaviour of the solution. They affect the mobility of ions within that solution, fundamentally affecting its behaviour and changing the way in which it behaves. So we think of ideal solutions where the concentration is equal to the activity, but very few solutions are ideal. And we've demonstrated this by discussing the presence of the ionic atmosphere. So fundamentally, we need to use something different. We use the activity to summarise all of these effects. The activity A and the activity coefficient, which is simply a way of scaling our concentration to give us the overall activity. To explore this in more depth, we need to go over some basic principles. Firstly, we ignore water. This seems daft. We've been talking all about the solutions, but we just treat water as an unstructured, uniform material providing a relative permittivity of 78. That's all we consider water to be for the purposes of exploring solution activity. We assume the only thing that affects the interactions is the electrostatic interactions. So we completely ignore any dispersion forces, any of these London forces that might otherwise cause attraction. Ionic attraction or electrostatic attraction is far stronger and would far outweigh any dispersion forces that might be there. We also need to assume a spherically symmetric ionic atmosphere. So whenever we look at this ionic atmosphere, we have to assume it's spherically symmetric. Otherwise, our exploration of solution activity breaks down. Using these assumptions, we can determine activities using the Debye-Hückel theory. We'll cover more on this later on, but it's important to flag it here so that we know to come back to it later on. We need to now consider the ionic strength of solutions. The ionic strength affects the activity, so the stronger the ion solution is, the more it affects that activity. The ionic strength can be found simply by summing up the square of all the charges multiplied by the concentration. This is simply a formula that we use to calculate ionic strength. It depends on the concentration of each ion, moles per kilogram again, remember, but it also depends on the charge on the ions themselves. And this can have a great effect depending on what ions and what concentration we're using. So if we consider 1 molal NaCl, if we simply substitute the values in, so we think, okay, well let's deal with the sodium first. We've got a +1 charge, we square that, multiply it by the concentration, divided by the standard concentration, and then we add on to this the charge of the chloride and square that. We end up with an ionic strength of 1 for 1 molar sodium chloride. Okay, that's fine. For magnesium chloride, we're going to look at half the concentration, so we're going to look at half molal's concentration. But if we examine this equation, we find that if we take the charge on the magnesium, the charge on the chloride, now remember there's twice as much chloride in concentration as there is magnesium, so we've doubled up here, we find that we end up with an overall ionic strength which is higher than the sodium chloride despite having a concentration which is half. So this is an important consideration, this ionic strength, because it affects other measurements we're going to do further down the line. Whenever we think of an activity, we think of the mean activity of a solution. Remember, it's impossible to measure these things in isolation because these anions and cations coexist. So that means anytime we determine an activity, what we're really looking at is the combined activity of the cation and the anion. So we cannot separate their effects. So fundamentally, we're looking at solution activity as a net effect of these two things combining. And the mean activity coefficient covers the entire solution. So if we have a different salt with different components, we would expect the mean activity to combine in this manner, where we simply have an algebraic relationship between the mean activity of each of the components combining to give us that mean activity of solution. But how does the activity coefficient vary with concentration? We need to understand a little bit about how this works. So this introduces the law known as the Debye-Hückel limiting law. Its expression is fairly straightforward, where we simply combine the product of the charges and the ionic strength, and we get an expression for the mean activity of solution. So it's a fairly straightforward thing to measure. We simply determine the ionic strength, we look at the charges, and that gives us a way to predict the mean activity of the solution. Looking at this, we should see that, well, we have a fairly straightforward relationship. For a given solution, we would have a fixed ionic strength, we'd have a fixed relationship between the charges, which means that we should have a straight line plot. And we see that this is indeed the case. By plotting log gamma, we see that we have a straight line relationship for different electrolytes. And that's fine, that's fairly straightforward. Remember that the concentration effect comes into the ionic strength. So whenever we think about changing concentration, that's what we're varying. This A term, whenever we're considering a solvent, this will be a particular scaling factor for a given solvent. For water, it's 0.509 at 25 Celsius. However, this law only works at low concentrations. And when we say low, we mean as low as 1,000th molal. So a very small concentration indeed. But what we see is that as I approaches zero, so as this ionic strength approaches zero, so as the concentration is approaching zero, log gamma, so this term here, approaches zero, which must mean that gamma approaches 1. Remember, this is a power of 10. So if log base 10 is 0, that means that the number we're looking at tends to 1. And that certainly aligns with this graph. So as we reduce the concentration, reduce the ratio there, we get close to a log gamma of 0, which means gamma must be approaching 1. That means the activity is approaching the measured concentration. As we increase the concentration, the activity decreases. The reason for this is that at higher concentrations, ion-ion interactions become much more significant. The long-range effects of ionic interactions affect the way in which the solution behaves. Exploring the Debye-Hückel limiting law further, we need to think about what the limits are in this. So what can we look at? Well, let's think about what happens with higher ionic charges. The higher the charge, the faster the ionic strength grows, but also the faster this component grows as well. We get a faster and faster deviation from theory. So if we look at this particular one, we're looking at sodium chloride, magnesium sulfate, and magnesium chloride. The green one here represents low ionic charge, while the red one represents very high ionic charge. We see this deviation becoming more and more prevalent for highly charged ions. The theory predicts a negative logarithm. We see these cropping up everywhere in chemistry, which must mean that our activity coefficient must be less than 1. So because the activity is less than 1, that means that these ions which are surrounded by this ionic atmosphere have a lower chemical potential when the gamma is less than 1. However, as we said, this atmosphere model only applies at very low concentrations. When we get to high concentrations, this Debye-Hückel limiting law starts to break down. So as we increase the ionic strength I, log gamma becomes more and more negative, but then it turns around. And what we find is that when we measure it, at high ionic strengths, log gamma actually increases. It becomes greater than 1. So what does that mean for our activity coefficient? So this means the effective concentration, the activity, has become greater than the actual concentration in solution. But how can this possibly be the case? How can we suddenly be in a place where we have a greater effective concentration? Well, in order to understand what's going on, we need to think about what's happened to the solvent. It's useful to think, where is the water? So if we look at 1 molar lithium chloride, so we've got lithium chloride, which is the green curve, it's the most rapidly deviating model here. Lithium chloride has, when we solvate it, we find that we have 5 water molecules to each lithium ion in a primary hydration cell, while the chloride has 1 water molecule in each hydration shell. So if we look at 1 mole of lithium chloride, around about 10% of the water is tied up. It's locked into these primary hydration shells. So what that means is that we've affected significantly the activity of the water. The effective concentration of water is reduced. Because we've effectively reduced the concentration of water, that means we must effectively increase the concentration of ions. And this seems like a very weird thing, but we have to consider the effect of concentration of water and the effect of concentration of our ions. And we need to ask the question, is free water in considerable excess? So the amount of water free in solution, not tied up in solvation shells, we have to make sure it is in considerable excess. Otherwise, we will start to see this deviation, which allows for an activity which is greater than the actual concentration. The effect is greatest for lithium. So the lithium cation is the smallest of the group 1 ions. Because it's small, it's got the highest field around it, and that allows it to hold much more water in a primary solvation shell than either of sodium or potassium. And this allows it to hold much more water in a primary solvation shell than either of sodium or potassium because of that extremely high field. But remember, for any of this to work, we need to make sure there's sufficient free water. Remember, water not tied up in solvation shells, because that's required to stabilize our ions, because it forms an intrinsic part of ionic atmospheres, letting those ions freely move around. If there's a significant difference in the amount of free water available, that causes this great deviation from ideal behavior. And we see, as I say, we see this most for lithium chloride and less for others, but we still see the presence of this deviation caused by that change in activity of the water. So in summary, we cannot ignore the effect of solvents in our solutions. They're an intrinsic part of the system. So without the solvent, we wouldn't have a solution. But the presence of the solvent affects the effective concentration of the analyte. So as we tie up some solvent molecules with the solvation shells, we see that we get a change in the activity of our analyte. As we increase the ionic strength of the solution, remember that's related to the charge on the ions as well as their concentration. The ionic strength of solution is intrinsically linked to the concentrations via the formula we saw before, and it doesn't always scale linearly because we have to factor in the charges on the ions as well. Finally, through the formation of solvent shells, we find that there is an absence of free solvent. As we increase the concentration of our analyte, we have more and more solvent molecules tied up in these solvation shells, and that reduces the amount of free solvent available, which decreases the activity of the solvent, increasing the activity of our analyte.